So the next thing that we're going to be looking at is rational expressions. So what is a rational expression? It is anything that can be written as a fraction. Okay, what does this mean? It would be like P over Q. Okay, now we know a couple of things. We know that P is our numerator. Q is our denominator. And if Q equals 0, the fraction is undefined. If P equals Q, the fraction is equal to 1. We also know that if we're dividing, okay, that we flip the second fraction and we multiply, but we'll get to that in a few minutes. There are a few things that we know. We know that if we have P over Q, and we make it times K over K. So PK over QK, this is equal to 1. Okay, the K over K cancels. So K over K equals 1. And anything times 1 is equal to itself. Right? So essentially these K's are canceling. So P times K over Q times K is equal to 1 because, sorry, I didn't mean equal to 1. I meant equal to P over Q. I apologize for that. This is equal to P over Q. I apologize for that confusion. I was thinking K over K equals 1. So P times K over Q times K is equal to P over Q. And for similar reason, P over K over Q over K is also equal to 1. Is also equal to P over Q. Why do we say that? Let's put that over here. So if we work this out, P over K over Q over K, what we can do is we have fractions within fractions, and we're going to talk about this when we talk about complex fraction. This is called a complex fraction. Because it has a fraction inside of another fraction. Or a fraction in the numerator. In this case, and in the denominator. And we're going to talk about this when we divide as well. So there are a couple of times that these complex fractions come up. The idea is that we don't want a complex fraction. We want to get rid of this fraction in the denominator. So we can multiply by its reciprocal, similar to when we rationalized denominators, or, you know, when it had the radicals and we were getting rid of the radical, or when we had complex numbers and we were trying to get rid of the imaginary number in the denominator, we multiply by the conjugates. This is similar. We're multiplying by the reciprocal, and what that does for us is it gets rid of the denominator in the first place. So the q's cancel, the k's cancel, but what we do on bottom, we have to do on top so that we don't change the expression, right? If we multiply the fraction by 1, we already know from here we get the same expression. So we would have to do that over here as well. And then once again, the k's cancel, and what are we left with? P over q. A fraction, when we multiply straight across, okay, when we have fractions that we're multiplying, we multiply straight across. Remember that from the exponents unit when we were simplifying exponential expressions. Okay, let's apply some of this, okay? Let's use numbers. Let's say that we had 3 over 2 times 4 over 2. So when we multiply fractions, we're multiplying straight across. We get 3 times 4 over 2 times 2, which gives us 12 over 4, or 3. Okay, now you always want to reduce your fractions. Throughout all of these videos, I've said a few things. I've said mathematicians want to be simple, they want to be elegant. This has to do with being simple and elegant, okay? Always reduce. If we have 7 over 6 times 5 over 6, again, you multiply straight across when we deal with fractions or rational expressions. In this case, we got 35 over 36. We can't reduce, so we just leave it. Okay, so this is how it would work with numbers. Let's start looking at algebraic. Okay, so a couple of things to notice about algebraic. So this is going to come into play, that if the denominator is 0, the fraction is undefined. Okay, so let's talk about that for a second. Let's say that we have x squared minus 9 over x minus 3. Okay, this is important because we have to say x minus 3 is not equal to 0. And why? Because if x minus 3 equals 0, the expression is undefined. So the domain is, we would say x such that x is not equal to 3. Okay, you could put this in the interval notation as well. But we say that what the domain is, what we want to do is we want to say that the domain is any number except for 3. Okay, so we will be talking about domain throughout these, okay? And at some point, we're going to say, okay, well, let's assume that our answer is within the domain, assume that we're working within the domain, okay? So just one more thing to mention. A minus B over A minus B is equal to 1. If we were to flip the bottom, though, in other words, if we had A minus B over B minus A, that's equal to negative 1. Okay? As long as A is not equal to B. Because if A and B were equal, then if A and B were equal, then the problem would be that this would be over 0 and it would be undefined. So that's why we're saying as long as A is not equal to B. Okay? Why is this true? Think about it. Okay? Let's think about it in terms of numbers first. If you take 6 minus 3, that's equal to 3. But if you take 3 minus 6, that's equal to negative 3. If you take 6 minus 4, that's equal to 2. But if you take 4 minus 6, that's equal to negative 2. If you take 9 minus 3, that's equal to 6. But if you take 3 minus 9, that's equal to negative 6. If you look at it algebraically, A minus B is the same thing as negative B plus A by the commutative property. But that's also the same thing as negative B minus A, right? We could factor out a negative sign. And if we factor out a negative sign, we get the B minus A. So A minus B is the negative of B minus A. If you have 3 over negative 3, that's negative 1. If you have 2 over negative 2, that's negative 1. Okay, so 3 over negative 3 equals negative 1. 2 over negative 2 equals negative 1. And the same thing would hold true if the negative were in the numerator. Okay? So these are just some of the things that I want you to keep in mind. The next thing that we're going to talk about are the operations on rational expressions. So it's very similar to everything else that we've done, right? We have the typical addition, subtraction, multiplication, division. Here we also have reducing. Okay, so we can simplify a rational expression. So we're going to talk about that first, and then we're actually going to go into multiplication and division because that's a little bit less complicated than addition and subtraction, which have extra steps in there. Okay, so let's start with reducing a rational expression. Okay, so we already know that if we have something like we had 12 over 4 is equal to 3, right? Why is that equal to 3? That's because 12, if we go backwards, 12 is equal to 3 times 4, and then 4 is equal to 1 times 4, and these 4's cancel, so we just get 3. Okay, both 12 and 4 have a common factor. That common factor is 4. Okay. This is true of many fractions. If we were talking about numbers, if we had 27 over 18. Well, this can be reduced to 3 over 2. Why can it be reduced to 3 over 2? Because 27 is 9 times 3. And 18 is 9 times 2. The 9s will go away, and we have 3 and 2. So 27 and 18 have a common factor of 9. So we're looking for common factors that we can then cancel out. The same is true when we work with an algebraic expression. So let's take an example, and we'll show you how to do it using that example, and then we'll do a whole bunch of examples that you can work with both on your own and going through the video, okay? So let's say that we have y squared minus 5y minus 6 over y squared minus 1. Okay. One important thing to remember. Order of operations tells us, I'm going to put this in purple. We cannot cancel a y squared here. Okay? We cannot cancel a y squared. The numerator and the denominator are both in parentheses, so we cannot just cancel anything at this point. We have an invisible parentheses. This was in one of your first problem sets. Okay. So we can't just divide. Okay, so what do we have to do? We have to factor first. So we have to factor the numerator, we have to factor the denominator. Okay. So y squared minus 5y minus 6. What we're looking for, this is quadratic, so we're looking for two numbers that multiply to negative 6 and add to negative 5. And those two numbers are negative 6 and 1. So this is equal to y minus 6 times y plus 1. Okay, now y squared minus 1 is also factorable. This is equal to, sorry, this is a square. Y squared minus 1 is equal to y plus 1 times y minus 1. This is a difference of squares. Okay, if you remember from quadratics, we said that that is a squared minus b squared is equal to a minus b times a plus b. Okay, so what does that mean here? What that means is that we can put this in here, y minus 6 times y plus 1. And then on bottom, we have y plus 1 times y minus 1. Well, we know that if we have the same thing on the top and on the bottom, it goes away because it's equal to 1. So the y plus 1 cancels. And what does that mean? That means that this is the same thing as y minus 6 over y minus 1. It also means that the domain in this case, domain is y because we have a y in our fraction and not an x. So the domain is y can't be 0, y can't be 1, and y can't be negative 1. Okay, the denominator can't be 0. And remember, you're talking about the denominator of the original fraction or the original expression. Okay, so we're looking at this denominator here. When it's factored, it's easy to tell, but you could solve this for 0 as well. If y were negative 1, the whole thing would be 0, because this would be 0. Anything times 0 is 0. And if y were equal to 1, then this part of the expression would be 0. Anything times 0 is 0. And the denominator would be 0. So you're looking at the original, not at the reduced. Okay? Always the original. Okay, so what does this mean? It means that reducing is a two-step process. The first thing that you're going to do is you're going to factor the numerator and the denominator. You're going to look for quadratics. You're going to look for differences of squares. You're going to look for a common factor in every term. And you'll see examples of this. This is not the case up here. Every term did not have a common factor, right? So we didn't use that. But you'll see examples of when we do use it. Okay, so these are the three major things that you're looking for. Once you factor, you can reduce by canceling factors and I'm going to underline factors, shared by the numerator and denominator. And I'll remind you to pay attention to the order of operations. Factors are when we can multiply by that. Notice the y squared is not being multiplied here. We're subtracting. That's why we can't cancel it. These are not factors. Y squared is not a factor of y squared minus 5y minus 6. Y squared is not a factor of y squared minus 1. It's being added or subtracted. Factors are multiplied. Okay, so that's why I say pay attention to the order of operations. Just because something is shared by the numerator and the denominator, it doesn't mean it's a factor. The y plus 1s can get canceled because the y plus 1, that whole expression, is being multiplied by y minus 6. This y plus 1, the whole expression, is being multiplied by y minus 1. And even though the numerator and the denominator are in parentheses, multiplication and division are interchangeable in the order of operations. So we can divide before we multiply in this case. Okay. Okay. Let's do a whole bunch of examples here. And at this point, you learned everything that you need to learn about reducing. So I would encourage you to stop the video every time that I introduce a new example. Try it yourself, and then you can restart it and make sure that you did it correctly. Okay? So let's say that we have 2a squared minus 8 over 4a squared minus 12a plus 8. Okay. You have a few options here. You can start canceling. Okay, sorry, you can start factoring at this point. And you can either factor this quadratic as is, okay, where you try and factor 2a squared minus 8, or I would always, the very first thing that I would always do is this one. Look for common factor. Okay, so always try this first. And the reason why I say this is that this simplifies the factoring process quite a bit. Okay, so it turns out that in this problem, everything is divisible by 2. So we could divide everything by 2 and save ourselves a lot of time. And you'll see why. So let's divide everything by 2 first. Okay, and again, you can do this 2 ways. You can either just start, okay, everything is divisible by 2. It's not just the numerator, but also everything in the denominator is divisible by 2. So we can actually go through and cancel every 2. We can make this a squared. We can make this a 4. We can make this a 2a squared. This is 6a, and this a 4, okay? I'm actually going to do it in a slightly different way just so that you can see what's going on here, okay? So it would be perfectly acceptable to write a squared minus 4 over 2a squared minus 6a plus 4. And then factor again. Okay, I'm going to write it by actually showing you the 2 factored out. So 2 times a squared minus 4 over 2 times 2a squared minus 6a. Sorry, by factoring out a 4 here instead of a 2. So making this 4 times a squared minus 3a. Plus 4. Sorry, plus 1. I apologize. Okay. The reason why I'm doing this and factoring out the 4 on the bottom is that this denominator is actually not just divisible by 2. It's also divisible by 4. And if you factor out the 4 instead of just a 2, what's good about it is that this a squared has a coefficient of 1, which makes it much easier to factor. Okay. I am not going to go through factoring here with you in this video. If you have questions about how to factor, please go back to the video on factoring quadratics. Okay, so I'm not going to repeat everything. This a squared minus 4 is a difference of squares. So we could say that this is 2 times a plus 2 times a minus 2. And now down here we have 4, and a squared minus 3a plus 1 factors to a minus 2 times a minus 1. Okay, so from here we could cancel common factors. So the a minus 2 is going to cancel. Because it's shared by both the numerator and the denominator. And this 2 and this 4 can actually get reduced to 1/2. Right? So what are we left with? Our final answer is just a plus 2 over 2 times a minus 1. Okay, and the domain, I will not ask you to always write the domain, but we're writing it here just so that you get accustomed to the idea that there is a domain. A can't be 2 and a can't be 1. So we're taking that from the denominator here. It's always easiest to find the domain after you factor. Not after you cancel, but after you factor. The only thing that would have been different if you went straight to here, as opposed to doing it this way, is that you either would have factored out the 2 at this point and then gotten a minus 2 times a minus 1, or you might have factored this and gotten something like 2a minus 4 times a minus 1, and then you would have had to factor out a 2 at some point anyway. Okay. If you didn't follow that, don't worry so much about it, because all you need to be able to do is do it in one method. Okay, let's try a few more. The reducing, by the way, is the biggest aspect of all of the other operations on rational expressions, so we're going to spend the most time on it. Okay? Okay, so next example, x squared minus 25 over 5 minus x. So again, we factor. x squared minus 25 is a difference of squares. I want you to notice that there is no common factor to every single term. 5 is only works for 25 and 5. The x's, it doesn't work for. So we can't cancel anything here at this point. Okay. So we have a difference of squares. X squared minus 25 is x plus 5 times x minus 5. 5 minus x is already in its simplest form. Okay, so now what? Well, we know from earlier that x minus 5 over 5 minus x is negative 1. Okay, how do we know that? A minus b over b minus a is equal to negative 1. Now, if everything in the numerator cancels, you're left with a 1 in the numerator. If everything in the denominator cancels, you're left with a 1 in the denominator. And remember, if there's a 1 in the denominator, it's as if the denominator doesn't exist at all. So this is just equal to negative times x plus 5. And you can say that this is negative x minus 5. You do not have to. Either one of these is fine. Because the idea is to reduce. So in both cases, we have reduced as much as possible. Okay, and once again, our domain x cannot equal 5 here. Because if x were equal to 5, 5 minus x would be 0. Okay, let's take another one. Let's say that we have a to the 4th minus 81 over a minus 3. Okay, again, 3 can't get canceled. We have to factor. A to the 4th minus 81 is a difference of squares. This is a squared minus 9 times a squared plus 9 over a minus 3. Now here's the thing though, we're not done yet. Because a squared minus 9 is also a difference of squares. So we could factor again, which is rare. Okay, this is not typical, this is rare. But a squared minus 9 is a plus 3 times a minus 3. That a squared plus 9 has to be left alone. It is not a difference. Okay, there is no way to factor a sum of squares. The a minus 3 cancels. Sorry, I meant to do that in blue so that you could see it, but okay. And what we're left with here is a plus 3 times a squared plus 9. You do not need to multiply this. Okay, the whole point is just to reduce. And if you've reduced, you're done. Okay. So our domain here is just that a can't be 3. Okay. And I will warn you, this is a great example of if you went to this and you said, okay, I'm done, you would be incorrect. So you should always make sure that you have factored completely before declaring you're done. And the best way to do that is to go through that list before you box your answer, right? Make sure that you don't have a quadratic that can be factored. Make sure that you don't have a difference of squares. Make sure that there's no common factor to every term in any individual factor. Okay, let's take another one. We'll do two more, and then we're moving on to multiplication. So let's say that we have 1 minus a squared over a squared minus 2a plus 1. Okay. So certainly we see a quadratic here, so we're going to try and factor that. We also see a difference of squares. 1 minus a squared is a difference of squares. 1 is a perfect square, a squared is a perfect square. So that can be factored to 1 plus a times 1 minus a. And a squared plus a squared minus 2a plus 1 can be factored into a minus 1 times a minus 1. Okay, so what happens here? Well, the only thing that can be reduced here is that we see a 1 minus a and a minus 1. And we know that that's a negative 1 because they're on separate sides they're flipped on the side of the subtraction. 1 plus a and a minus 1 you can't do anything with. Okay, there's nothing to do. So this is just equal to negative 1 plus a. You can distribute the negative, but you don't have to, over a minus 1. Where the domain is a not equal to 1. Okay, let's take one more. So we have x minus 4 over x squared minus 6x plus 8. So x minus 4 is not factorable. It's not a quadratic. The only thing that you can do with a linear is look for a term that both terms have in common. Look for a factor that both terms have in common. There's nothing. X and 4 don't share any common factors. So x minus 4 stays the same. An example of if it did were like this 2a squared minus 8, where the a squared and the 8 both have a common factor of 2. If this had been 2x minus 8, you would have been able to divide both by 2 and factor it out, but it doesn't. So x minus 4 just stays as it is. And then x squared minus 6x minus 8 can be factored to x minus 4 times x minus 2. The x minus 4s will cancel here. And what we are left with in the numerator is a 1. It's not that the numerator goes away. You can't have something in the numerator and then all of a sudden it's in the, you can't have something in the denominator and all of a sudden it's in the numerator. In other words, the most common pitfall is that students will cancel out the x minus 4 and then say that this is equal to x minus 2. We can't do that. X minus 2 is in the denominator. It stays where it is. So this is just 1 over x minus 2. And your domain, be careful here, is that x can't be 2, but it also can't be 4. So remember, look at the original fraction, okay, the original expression. Okay, we're going to take two examples of multiplication because multiplication is essentially reducing, okay? The only difference is that we have two expressions and we're essentially just extending the fraction bar. So when we multiply rational expressions, and this would be true of 2 rational expressions, 3 rational expressions, 10 rational expressions. You're extending the fraction bar. And you're reducing. Okay? Essentially, you're multiplying straight across. So let's take an example. Let's say that we have 3x minus 12 over x squared minus 4 times x squared plus 6x plus 8 over x minus 4. Now you can factor first and then multiply, or you can multiply and then factor. I tend to factor and then multiply. It makes no difference because it's essentially one step. Okay, so if we factor this, 3x minus 12, you're factoring each numerator and each denominator. So 3x minus 12, we can factor out a 3, okay? It has a common factor of 3. So what we get here is 3, and then when we factor out a 3, we're left with x minus 4. Now, if we factor the bottom of that fraction, it's a difference of squares. So that's x plus 2 times x minus 2. Then x squared plus 6x plus 8, that's x plus 4 times x plus 2. And then we have x minus 4. X minus 4 cannot be factored. Okay. And essentially what we're doing, not essentially, actually what we're doing is we're saying, okay, well now that this is all factored, we could just treat it as one fraction. If we wanted to multiply across beforehand, all we would be doing is just putting this in parentheses and this in parentheses and then factoring. Eventually you'll wind up with this. So I'm writing this as an extra step, but you do not have to. You can skip this. What does that mean? That means that this is equal to 3 times x minus 4 times x plus 4 times x plus 2 over x plus 2 times x minus 2 times x minus 4. Okay, notice when I put it as one fraction, everything gets put in parentheses. Why am I writing it like this? Just to make sure that you're okay with the fact that now we're just canceling. You have an x minus 4 on the top and an x minus 4 on the bottom, and an x plus 2 on the top and an x plus 2 on the bottom. You can go directly from here to this last step, to here. Okay, you do not have to you do not have to show this written as 1 because you've extended the line already. Okay. Or you can skip this and go straight to this step. So you can skip either one of these 2 steps, and that's fine. Okay. Just don't go straight from here to your final answer because I need to see how you factored. Okay. And that's it. And we're not really going to talk about domain with multiplication. We can. Okay. The domain would just be that it can't be 2, it can't be -2, and it can't be 4. But we're just not going to talk about domain with multiplication. Okay. Let's try one more example and then we'll move on to division. So we have y minus 3 over y squared minus 6y plus 9 times y minus 3 over 4. Okay. And again, the reason why I'm only doing 2 examples is because essentially you're reducing one big fraction. Okay. This is the same thing. We're going to factor the bottom. Y minus 3 is not factorable. It's a linear, there's no common factor. Y squared minus 6y plus 9 is y minus 3 times y minus 3. Then we have our y minus 3 over 4. We can extend our line. And again, I'm writing the extra step here. That means that we have y minus 3. Notice now it's in parentheses because I'm combining it with the other y minus 3. And then y minus 3 times y minus 3 times 4. Both of the y minus 3's cancel, leaving us with a 1 in the numerator. And our final answer is just 1 over 4. And that's it. Okay, let's talk about division. So division is same thing in terms of you're essentially just reducing. You have one extra step. Okay. The extra step here is that you need to get rid of a denominator. Okay, that's because division of rational expressions will get you this complex fraction where you have a fraction within a fraction. So for example, let's say that we had 3 over 7 divided by 6 over 5. Now, if we want to divide these expressions, what we want to do, what we're really doing is we're getting rid of the denominator, okay? We want to get rid of the fraction within the fraction. So what we're going to do is we're going to multiply the denominator by its reciprocal, because that cancels everything and we get rid of the denominator. But what we do on bottom, we have to do on top. So we have to multiply the top by 5 over 6 as well. So what does that mean? That means that when we do 3 over 7 divided by 6 over 5, that's really the same thing as doing 3 over 7 times 5 over 6, which is 15 over 42, which reduces. Okay, so what does that mean we're doing? When we divide, we are taking the numerator and multiplying by the reciprocal of the denominator. So if we have 2 over 3 divided by 8 over 5, this is the same thing as 2 over 3 times 5 over 8. So keep in mind that this division is the same thing as the fraction bar. Okay, this is what the fraction bar is. So what does that mean? That means that we get 10 over 24 and we reduce, this is 5 over 12. Okay, we took the reciprocal of the second fraction and multiplied. Only the second, and it has to be the second. Okay, you can't take the reciprocal of the first fraction. So let's take, again, a couple of examples. Okay. And again, we're just doing 2 examples here. Okay, the first one is going to be really straightforward. The second one is going to look a little bit different, but you're going to see that it doesn't change anything at all. Okay, I just want you to see something a little bit different. So a squared minus 5a plus 6 over a squared minus 2a minus 3 divided by a minus 5 over a squared plus 3a plus 2. Okay? So what are we doing here? Factor. Okay? So this is the easiest way to do it, to factor first. I like to factor first as opposed to multiplying first because it helps me keep the parentheses straight. Okay, it is completely up to you how you do it, as long as you get to that right answer in the end. So I factor, and then you take the reciprocal, or you could take the reciprocal and then factor it. It doesn't matter. Okay. So a squared minus 5a plus 6 factors to a minus 5 times a minus 1. I have this backwards, don't I? Hang on. Give me a second. I'm going to change this because I had it backwards. I'm going to say that it's a minus 6a plus 5. Sorry about that. I want to make it easy for you. A squared minus 6a plus 5. This is an a. Okay, a squared minus 6a plus 5. That's a minus 5 times a minus 1. Sorry about that. A minus 5 times a minus 1 over a minus 3 times a plus 1. Oops. And then, and you can flip it in the same step. I would be okay with that, okay? A minus 5 over here, it's a plus 2 times a plus 1. Okay, let's keep going. What is this equal to? We want to flip the second fraction. So what does that mean? That means that we wind up with a minus 5 times a minus 1 over a minus 3 times a plus 1 times, now we flip it, a plus 2 times a plus 1 over a minus 5. Okay, so we flipped it. Now at this point, so let's just write in here that we flipped the second fraction. And multiply. So at this point, I'm going to skip a step and I'm just going to cancel here. Okay? Because we're just extending our line. So a minus 5 cancels. A plus 1 cancels. And that's it. And that's okay. So what are we left with? Just a minus 1 times a minus 2. Sorry, times a plus 2. Over a minus 3. Okay, and again, I'm not going to bother with domain. Okay, let's try another one. This one is a combination of multiplication and division. So it's a little bit different because the factoring is different. 4x cubed over 7y squared. A lot of people would say this is much easier. Times 6z to the 5th over 5x to the 6th divided by 24z squared over 35x to the 6th. Okay, so what do? We take the reciprocal. What do we take the reciprocal of? This one, this 24z squared, 35x to the 6th. Right here. So this is 4x cubed over 7y squared times 6z to the 5th over 3x to the 6th times 35x to the 6th over 24z squared. Okay, so at this point, what do we do? Well, we multiply straight across, okay? You have some options here. I'm going to write this in two different ways. On the right side, I'm going to put it in blue. On the left, I'm going to use a different method, okay? So if we were to do this on the, what we could do is we could say, okay, let's multiply all of our constants. Well, 4 times 6 times 35 is equal to 840. And that's x cubed, z to the 5th, x to the 6th. And then on bottom, we have 7 times 3 times 24. That's 504. Y squared, x to the 6th, z squared. Sorry, that's a square. Okay, from here, what we would do is we would just simplify the x cubed and the x to the 6th and then simplify from there, okay? What did I mess up? This is not a 3, this is a 5. Which means that this is not 504. This actually winds up being 840. And it turns out that this makes it nice and simple because the 840 cancels. Okay? Now here's the thing though. These are big numbers and it doesn't always wind up so beautiful. So what we have to do, what you can do, so if this had been, let's say 840 over that 504, reducing those constants might have been much more difficult. So instead, what we can do is we could start reducing from the step that comes before with these 4s, 6s, 35, 7, 5, 24. And the way that you would do that is you would look for factors, okay, that those numbers have in common. So for example, 4 and 6 is 24. So 4 times 6 will cancel with the 24. 7 times 5 is 35. So 7 and 5 will cancel with the 35. And you don't have to do any of the multiplication, okay? So you can go straight to this step, which would give you x cubed z to the 5th times x to the 6th over y squared x to the 6th z squared. And then this is just a regular exponential expression. We combine the x's first on top, so we get x to the 9th, z to the 5th. On bottom, we get y squared, x to the 6th, z squared, and then we can subtract those exponents. So x to the 9th over x to the 6th is x cubed. Z to the 5th over z squared is z cubed. And then that y squared can stay on bottom. Okay. So just a reminder, what we did here is we combine horizontally. And then we combine vertically. This comes from our exponents unit. Okay, you just multiply the constants. But you can try reducing first. I'm not going to go through and do that here, but if you have questions, obviously send me an email. Okay? And that's it for today.